Okay, we're picking up where we left off in chapter 4, talking about oxidation reduction reactions in section 4. So we stopped before starting the part of section 4 on oxidation numbers. Okay, so oxidation numbers make it very easy to analyze any chemical reaction, and not just reactions in aqueous solution, reactions in any circumstance. Analyze a reaction for the redox characteristics of the reaction. So, is the reaction a redox reaction? If it is, which atoms of which compounds are involved in the redox process? How many electrons are transferred, and which atoms of which elements are oxidized and which are reduced? Okay, so in the first part of this section, we analyzed a few redox reactions. Okay, and what we did was we broke down the redox characteristics of these reactions manually. Okay, so for example, this first redox reaction here that we analyzed, it didn't occur in aqueous solution. So you had solid magnesium in an O2 gas environment, and this is at standard atmospheric pressure, but at higher than standard temperatures, you'll get a reaction between the magnesium atoms and the O2 molecules to where magnesium oxide, the ionic compound magnesium oxide solid, is produced. Okay, and so we analyzed this chemical reaction from the redox perspective by first looking at the reactant compounds. So we can see we have neutral magnesium atoms and neutral oxygen atoms, right? You have two neutral magnesium atoms, and there's one neutral O2 molecule, which is that contains two neutral oxygen atoms. Okay, now what do we finish with on the product side? Well, 2 units of magnesium oxide, the magnesium oxide ionic compound. But we know how ionic compounds work, but what they're composed of, it's a bond between ions. In this case, this is a bond between, you've got 2 magnesium 2 plus cations and 2 O2 minus anions. And so we can see clearly that this is a redox reaction. Electrons have shifted from their original positions or locations on the reactant side to some new positions or locations on the product side. Now, and specifically, you've got 2 neutral magnesium atoms, each transfer 2 electrons to a neutral oxygen atom to create 2 magnesium 2 plus cations and 2 O2 minus anions. So in total, you've got 4 electrons transferred here. 4 electrons transferred from 2 neutral magnesium atoms to 2 neutral oxygen atoms. But just for comparison, none of the precipitation or acid-base neutralization reactions that we discussed in section 2 and section 3 were redox reactions. So if we look here, this is the net ionic equation for the reaction in aqueous solution between potassium iodide and lead 2 nitrate. Okay, so the net ionic equation, this just gives you the chemical reaction that took place with respect to the dissolved ions. So we can see in the reactants, we start with lead 2 plus cations and I minus anions. And what do we end with? Okay, the ionic compound lead 2 iodide, which we know is just, this is a bond between lead 2 plus cations and I minus anions. So you can see we started and ended with the same ions. There's been no shifting or transferring of electrons in any sense here, going from the reactants to the products. So it's not a redox reaction. And we would see the same result of a non-redox reaction if we did this same kind of analysis with any of the acid-base neutralization reactions from the previous section. Okay, and so again, this redox reaction didn't take place in aqueous solution, but we looked at 2 other redox reactions that did take place in aqueous solution. So here you can see we've got solid zinc in a copper 2 sulfate aqueous solution that results in a chemical reaction taking place. And the corresponding net ionic equation for this reaction makes it clear that this is a redox reaction. And it also makes it clear what the specifics of the electron transfer is, right? You're starting with solid zinc, you're ending with zinc 2 plus, you're starting with copper 2 plus, you're ending with solid copper, right? That's a shifting of the positions or locations of electrons. Okay, same idea here with you've got solid copper in a silver nitrate aqueous solution and the corresponding net ionic equation where, again, we can see how this is clearly a redox reaction, right? You're going from copper to copper ions and then from silver ions to neutral silver. Okay, but one thing you might have noticed is that all three of these redox reactions contained at least one ionic compound. Okay, so the first reaction, you've got magnesium oxide. This second reaction, you had copper 2 sulfate and zinc 2 sulfate. Here you had silver nitrate and copper 2 nitrate. Okay, and so what you can think about is if an ionic compound is present in a chemical reaction, it makes it a lot easier to analyze the redox properties of the reaction because we can identify the ions bonded within an ionic compound. So in general, it's overall easier to track electrons in a chemical reaction that involves one or more ionic compounds, right? Okay, but a redox reaction in general isn't required to have any involvement with ionic compounds. Okay, so it says the definitions of oxidation and reduction in terms of loss and gain of electrons, so the definitions we discussed in the first part of this section, apply to the formation of ionic compounds such as magnesium oxide and the reduction of copper 2 plus ions by zinc. Yeah, that's two of the reactions we looked at. However, these definitions do not accurately characterize the formation of hydrogen chloride and sulfur dioxide. So H2 gas and Cl2 gas interact to form HCl gas, and then you have solid sulfur and O2 gas interact to form SO2 gas, right? So why are they giving these chemical reactions? Because there's no ionic compounds. And so if you think about it, these are all molecular compounds, or in the case of sulfur, you just have an atomic elemental form. And so they're saying that the way we looked at the meaning of oxidation and reduction in this first part of this section, those definitions didn't accurately characterize all possible redox reactions, in particular something like this. And they're mainly saying that because we talked about how electrons are transferred. They start off in one location or position in the reactants, and then when go into products, they're transferred. And this definition made sense when ionic compounds were involved because we know that ions are created by a full transfer of electrons. Electrons are fully transferred to form ions, right? And so that's what they're saying here. Because HCl and SO2 are not ionic but molecular compounds, no electrons are actually transferred in the formation of these compounds, right? So when it comes to a molecular compound, not an ionic compound, we know that molecules are made up of what are called covalent bonds, in which case electrons are shared between atoms, right? And so if we're starting with like H2 and Cl2, where you have electrons shared between the atoms in these molecules, and we're ending with HCl, we know there's no transfer of electrons involved going from reactants to products. There can't be because you have no ions involved, as was the case with when we were dealing with ionic compounds like magnesium oxide. Okay, but nevertheless, chemists find it convenient to treat these reactions as redox reactions because experimental measurements show that there is a partial transfer of electrons. So from H to Cl and HCl, and from S to O in SO2. So they're saying that there is a partial transfer of electrons from the H atoms to the Cl atoms to create HCl, and from the S atoms to the oxygen atoms to create SO2. Okay, but the issue is that it's more difficult to track electron shifting with respect to molecular compounds. It's not as easy as if you're dealing with ionic compounds. And so that's the whole purpose of oxidation numbers. oxidation numbers, once you know how to quickly assign them to the atoms of any compound, they make it very easy to characterize the redox characteristics of any chemical reaction, even if a reaction involves all molecular compounds. Okay, but now, so what are oxidation numbers? How do they work? How exactly are electrons transferred or repositioned in these reactions here? What are they talking about? They're saying that experimental measurements are showing that there is a partial transfer of electrons in these reactions. So what are they talking about? Okay, well, they're referring to a change in polarity. The idea is what chemists consider that it's not just that if there's a total transfer of electrons to create ions, that you're dealing with a redox reaction, even if there's a change of polarity going from reactant to product compounds in a chemical reaction, that's still considered a redox process, an electron shifting transfer process. Right? The idea here is that you started off with two neutral molecules, an H2 and a Cl2 molecule, and you ended up with a polar HCl molecule. The specifics of the polarity being a positive dipole on the hydrogen and a negative dipole on the chlorine. And so that's considered a redox process. Okay, so to keep track of electrons in redox reactions, it is useful to assign oxidation numbers to the reactants and products. An atom's oxidation number, also called its oxidation state, signifies the number of charges the atom would have in a molecule or an ionic compound if electrons were transferred completely. Okay, so the concept of oxidation numbers and how they're used to analyze redox properties of reactions is very simple. The challenging part is correctly assigning the oxidation numbers, which we're going to talk about in a few minutes. Okay, but the concept of oxidation numbers is this. It's what they just stated here. So let's say that you're presented with any chemical compound. Let's say it's a molecular compound like H2O. Okay, well, again, we know that while no molecular compounds are ionic, many are polar, like H2O. The H2O molecule is famous for its high degree of polarity. That's one of the main properties of H2O that makes it so essential to life. So you've got positive dipoles on the hydrogen atoms and a negative dipole, -2- dipole on the oxygen atom. Okay, so all we do with oxidation numbers is this. And note, this is purely done as a tool for analyzing redox reactions. That's it. This has no actual meaning in terms of physical reality. This is simply just a trick, a tool that's used to analyze redox reactions. In particular, when you're dealing with molecular compounds. Because we're going to see when we extend this definition of oxidation numbers to ionic compounds, it's really trivial. So this is really more about molecular compounds with these chemical bonds that involve the sharing of electrons. Okay, so if a chemical compound has any degree of polarity whatsoever, so H2O is known for its high degree of polarity, but we can even think about something like NO2, which has more of a closer to linear shape, but that's not really important for oxidation numbers. Okay, so you've got a negative dipoles here, a positive dipole here. Okay, but the difference in electronegativity between oxygen and hydrogen is a good bit larger than the difference in electronegativity between nitrogen and oxygen. So H2O is a much more polar molecule than N2O. Okay, but with oxidation numbers, when it comes to oxidation numbers, the degree of polarity doesn't matter at all. You're just asking the question, is this molecule polar or isn't? That's the first thing you're going to ask. Polar to any degree. Okay, and so what we do is we say that if a compound has any degree of polarity, then we assume that hypothetically all of the electrons that are the cause of that polarity are fully transferred to the corresponding atoms in which those electrons are skewed to create these hypothetical ions. And whatever the charge is on these hypothetical ions, that number, that charge number, that's the oxidation number that's assigned to the atom. And that's it. That's it. And so what you can think about is that if, when presented with any chemical compound, if you had, it automatically had some inside knowledge of the polarity of that molecular compound that you're presented with, then assigning the oxidation numbers would be very, very simple. Because, okay, here for H2O, we know this is a polar molecule, and we know that the nature of the polarity is that you've got the oxygen atom, the more electronegative oxygen atom with respect to hydrogen, is pulling the lone electron of this hydrogen towards it, and the lone electron of this hydrogen towards it. That's it. That's what's causing this -2 polarity here and positive polarity here. It's called a polarity because it's not a full transfer of charge. It's just a skew of charge. Okay, but when it comes to oxidation numbers, what we do is we hypothetically assume that the electrons that are causing that polarity are fully transferred. So we act like, okay, each of these electrons from the hydrogen, from each hydrogen, is transferred fully to the oxygen. And so what would these hypothetical ions, what would their charges be? Well, this would be -2, this would be +1, and this would be +1. And that's it. That's the oxidation numbers. That is it. And then here, you've got 2 electrons being pulled towards each oxygen from the nitrogen. It's just a skew. It's a polarity. But the degree of the polarity is much less than the degree of the polarity here. But that doesn't matter. The degree of the polarity doesn't matter when it comes to oxidation numbers. You put, if this hypothetical ion that the oxygen would be -2, this would be a +4. And that's the oxidation numbers. That's it. Okay, and you might be a little confused in thinking, so the oxidation numbers, you say that, well, if this is much less polar, much less polar than H2O, then how are you assigning a full charge as an oxidation number here? Well, okay, the reason is because the reason why the polarity of the molecule doesn't matter with respect to oxidation numbers is it's because of the whole purpose of oxidation numbers. It's just a tool. It's a tool that helps us to track where electrons have shifted in a chemical reaction. That's it. We don't care about the degree of the shift. We just want to know, okay, did we start with a neutral oxygen, let's say, with no polarity, and then we ended with electrons being more skewed towards oxygens. So we could see how the electrons have shifted. That's it. Okay, so for example, let's take a look at the use of oxidation numbers with these 2 reactions here. Okay, first we had H2 gas and Cl2 gas mixed together, and they chemically react to form HCl gas. Okay, so the idea is once you're efficient with assigning oxidation numbers, you would go through and quickly assign the numbers shown here. Okay, so in the reactant side, we can see that the H2 and the Cl2 molecules both have a 0 on top. Okay, so what does this mean, this assignment of oxidation number of 0 to these molecules? Well, okay, this is saying that each of the hydrogen atoms in H2 has an oxidation number of 0, and each of the chlorine atoms in Cl2 has an oxidation number of 0. Okay, and so based on what we just learned as the meaning of oxidation numbers, what do these zeros mean? Well, okay, so if a compound has any degree of polarity whatsoever, we assume a full transfer of the electrons associated with that polarity, right? That's how oxidation numbers work. But with these 2 elemental forms here, there isn't going to be any polarity. There's no polarity associated with these molecules. How could there be? You can't have any kind of permanent shifting of electrons in a molecule or compounds, like a polarity, without different elements present. Because it's the differences in the number of protons in the nucleuses, and the number of electrons in the electron clouds that's going to cause the polarity. And so if there's no polarity at all, then the number of electrons that are hypothetically transferred is 0. Therefore, in these cases, the hypothetical ions that are created are neutral. There actually isn't any hypothetical ions created. So the oxidation number, the charge on the quote-unquote ion is 0. And that's the oxidation number. Okay, now HCl is a polar molecule. The more electronegative chlorine atom pulls the lone electron and the hydrogen towards it. So assuming a full hypothetical transfer of this electron all the way to the chlorine, you would have an H+1 ion and a Cl-1 ion. So there's the oxidation numbers. Okay, and so with the oxidation numbers assigned, how does this help us to analyze the redox properties of this reaction? Well, okay, at a quick glance, we just compare oxidation numbers of corresponding elements in the reactants and products. If there is any change in oxidation number whatsoever between reactant and product elements, you're analyzing the same element on each side, then the reaction is a redox reaction. Any change at all. If there's no change, then it's not a redox reaction. Okay, so we can see that the hydrogen atoms go from a 0 oxidation state in the reactants to a +1 oxidation state in the products. So there's just one change in oxidation number. So this is a redox reaction. It doesn't matter. It's not like the oxidation number has to change by a certain amount, or you have to have a certain number of elements have their oxidation numbers change. Once you see just one change, and no matter what the degree of that change is in oxidation number, then you know it's a redox reaction. As opposed to, for example, the reaction in aqueous solution between barium chloride and sodium sulfate. And here's the net ionic equation for this reaction. So the oxidation number of the barium 2 plus cation is going to be +2. And why is this? Well, as I mentioned, you can see how the extension of the definition of oxidation numbers to ions is trivial, because in that case, the electrons are actually fully transferred. So it's not even a hypothetical ion. It actually is an ion. So you just put the charge of the ion itself. Because remember, the whole purpose of oxidation numbers is just to track electrons. It's just like a tracking device. Well, it's easy to track electrons in an actual ion because all the electrons are fully transferred or fully removed from that atom. Okay, the sulfate, you've got -2 on the oxygens and +6 on the sulfur. And then in the products, you just have here a bond between barium 2 plus, so this is still +2, and SO4 2 minus, so this is still +6 and -2 on each of the oxygens. So you can see there you go. There's been no change in oxidation number with respect to any of these elements going from the reactants to products whatsoever. This is not a redox reaction. And really, all the oxidation numbers are telling you is that in this case, there's been no shifting of electrons, repositioning of electrons with respect to the different nucleuses of the atoms whatsoever. Right here, we had like a neutral clustering of electrons around hydrogen and chlorine atoms, and now go into the products, we get a little bit of a shift. We have electrons more skewed towards the chlorine atoms and more moved away from the hydrogen atoms. That's it. And so we consider that a redox reaction. Any shifting, rearranging of electrons as a result of a chemical reaction is considered a redox reaction. And here you can clearly see that there's been no repositioning, realigning of electrons. Okay, this next reaction, you've got solid sulfur in an O2 gas environment. A reaction takes place, and what you end up with is SO2 gas. So neutral elemental sulfur atoms will have an oxidation number of 0. A neutral O2 molecule, each oxygen atom in the molecule is going to have an oxidation number of 0. With SO2, the more electronegative oxygen atoms will pull 2 electrons each from sulfur towards it to create some polarity, but we assume a hypothetical full transfer of those electrons for the sake of oxidation numbers, and we get a -2 on each oxygen, and a +4 on the sulfur. And there we go. Okay, so this is a redox reaction, an oxidation-reduction reaction, because the oxidation numbers with respect to sulfur atoms and oxygen atoms in the reactants change when you go to the products. You go from 0 to +4 here and 0 to -2 here. Okay, but also just note that it's not like if you were dealing with a more complex reaction that had a large number of reactants and a large number of products. It's not like every single element involved has to have a change in oxidation number, like we saw with these two reactions. No, these were just simple examples, right? Every single atom involved in these reactions had a change in oxidation number. No, you could have a redox reaction where there's certain elements aren't oxidized or reduced. There's no change in oxidation number of those elements. They aren't involved in the redox process. As long as there's just at least one element being oxidized, and therefore there would have to be some other element being reduced, so just a pair of elements in this entire reaction, this big reaction, just these two elements being oxidized and reduced, then it's a redox reaction. Okay, now the specifics here of the redox process that the oxidation numbers illustrate is that you've got these single sulfur atoms and these single O2 molecules, right? The coefficients are 1. This is balanced. The O2 molecule is going to split up into two neutral oxygen atoms. So what you really have is neutral sulfur atoms and two neutral oxygen atoms. Okay, now in the process, there's a transferring, but really more of when you use the word transfer, that's implying you're talking about ions, so more of a shifting of electrons, specifically a shifting of 2 electrons from the single sulfur atom towards one of the oxygen atoms, and a shifting of another 2 electrons from that same sulfur atom towards the other oxygen atom. And then a bond gets created, the SO2 bond, that has a polarity in the sense of 4 electrons shifted away from the sulfur and 2 electrons shifted towards each of the oxygens. Okay, so it says that the numbers above the element symbols are the oxidation numbers. In both of the reactions shown, there is no charge on the atoms in the reactant molecules. Thus, their oxidation number is 0. For the product molecules, however, it is assumed that complete electron transfer has taken place and that atoms have gained or lost electrons. The oxidation numbers reflect the number of electrons transferred. Yes, here they're just explaining the meaning of oxidation numbers. Okay, oxidation numbers enable us to identify elements that are oxidized and reduced at a glance. The elements that show an increase in oxidation number, hydrogen and sulfur in the preceding examples, are oxidized. Chlorine and oxygen are reduced, so their oxidation numbers show a decrease from their initial values. Note that the sum of the oxidation numbers of H and Cl in HCl, the plus and the -1, is 0. Likewise, if we add the oxidation numbers of the sulfur +4 and the 2 oxygen atoms, so 2 times -2 is -4, then the total is 0. The reason is that HCl and SO2 molecules are neutral, so the charges must cancel. Yeah, so here they're just explaining how the oxidation numbers enable us to, at a glance, once you're able to quickly assign the oxidation numbers, then you can, again, at a glance, see the specifics of, well, first of all, is it a redox reaction? And then if it is, what are the specifics of the redox process? Like we broke it down here, each of the neutral oxygen atoms and a neutral sulfur atom, the sulfur, there's a shifting of 2 electrons each from the sulfur, etc. Right? It makes it very easy to analyze how electrons have shifted in a redox reaction, how many electrons have shifted, and from which atoms to which atoms are oxidized and which atoms are reduced, and to what degree, how many electrons. Right? Now, they also mentioned how you can think about that it wouldn't make sense in these cases. We couldn't have had a certain oxidation number associated with a certain atom change without a corresponding opposite change in oxidation number of some other atom. right? The hydrogen oxidation number increased by 1, going from the reactants to products. So there has to be some other atom that had a decrease in oxidation number by 1. And why is that? Well, because the electrons had to shift somewhere. The electrons couldn't just disappear, right? You had one electron shifted away from each of the hydrogen atoms in the reactants here. And what was that one electron shifted towards? Each of the chlorine atoms, right? Here you had 4 electrons shifted away from each of the neutral sulfur atoms. Okay, so where did those 4 electrons go? Okay, well, they went each to a neutral oxygen atom. Okay? So now that we have a clear understanding of what oxidation numbers are and why we use them, the next step is to learn how, when given any molecule or compound, how do we assign oxidation numbers to the different atoms of the compound, right? What are the rules? What are the steps that we use to allow us to quickly assign the oxidation numbers to every atom in any given compound? And that's what we're going to talk about in the next video.